So our next speaker is Adam Cahill from the Cornell University. His major is plasma physics. His advisor is David Hammer. He did his practicum at Los Alamos National Laboratory, and his presentation is on diagnosis of an azimuthally symmetric plasma by means of absorption spectroscopy.
But yes, so I will actually be talking about how I'm studying exploding single wires by using X-ray absorption spectroscopy. And I work in the Laboratory of Plasma Studies at Cornell University. So quickly, I'm going to talk about what pulse power is, why we need it, and how we use it at Cornell. So in case anybody isn't familiar with how these systems work, we'll take a brief overview of that. Then we'll get into the real motivation for this work and why we think it had some value. We'll talk about the experimental setups that have been used, go through a few results, and then finally we'll finish with where our current efforts lie and what we're going to be doing going forward. So high energy density experiments, they really require this pulse power kind of technology because we want to get to interesting physical states. That takes a lot of energy, but we need to do it very, very quickly so that we avoid any sort of energy dissipation in our systems. So what we do is we store energy over very long periods of time. By long, I mean minutes. And then we deposit that into our sample as rapidly as possible. So some examples would be like lasers that charge up capacitor banks to fire their flash lamps and then get photons out. We use Marx banks so that we'll charge up our capacitor and then discharge electrical currents into our samples. And linear transformer drivers are also a sort of newer sort of technology that's coming around now. So in this simplified schematic here, what we would initially do is close this switch to charge the capacitance in the middle, and that takes a long time. And then once it gets up to its full charge, we'll open this switch and then close this one, and we'll allow the current to flow as quickly as possible through our load. Now, just doing it like this doesn't really get you as far as you want to go. So in the XP generator that I use at Cornell, we have a Marx bank that's composed of 10 capacitors, and we store a total of approximately 15 kilojoules in that bank. And those are represented by C sub Marx on the left. What we'll do is we'll charge all those capacitors in parallel to about 40,000 volts. And then when we go to fire the machine, a few switches will close, and it will rearrange the capacitors into a series configuration. So we go from 40,000 volts to 400,000 volts. Let's see. This switch closes, and then we'll move current into the ISC, or intermediate storage capacitor. That happens on the order of hundreds of nanoseconds. Right as that capacitor reaches full charge, the gas switch closes. And then we dump charge into the pulse-forming line, or PFL. That happens in approximately 200 nanoseconds. And then right as that hits peak voltage, the water switches will close, and that moves the current finally into the load. That happens in a 50 nanosecond rise time, and we're able to deliver about 500 kiloamps of current. So that's what actually creates our plasmas. So once you have all that current, what do you do with it? The simplest thing to do is to create a Z-pinch. So we just run current through a fine wire. By fine, I mean tens of microns in diameter. And so what happens is this current heats the core, or heats the wire. We go from solid to liquid to gas very, very quickly. And then eventually we ionize the material and form this low-density corona around the dense core. This corona carries a large majority of the current. And what happens is that the self-imposed magnetic field confines and starts to compress the plasma. And eventually you develop instabilities. The easiest way to think about these is to consider that along this fine wire, the diameter is not perfectly uniform when the corona forms, and so we have some regions that have a slightly smaller radius. At those slightly smaller radii, we have larger magnetic fields. The larger magnetic fields do more compression, so we get even smaller radii, and we get kind of a positive feedback loop that runs away. Eventually, the compression gets to a point where we develop hotspots somewhere along the length of this wire. These hotspots are roughly a micron in size and can get up to 1 keV in temperature. And they release large bursts of X-ray somewhere along the length of the wire, which is typically a centimeter long. So if you just want to study X-rays, that's fine, because you're getting a lot of X-rays out. But if you want to do anything diagnostic with them, you don't know where the X-rays are going to show up, and so that's kind of a problem. To solve that problem, you go to something called an X-pinch, which is essentially just two wires running parallel to each other that you then twist to form an X. It's very creatively named. And so what this does is this kind of concentrates all of the current through that crossing point. And so at that crossing point, we have very high current densities, and we have a very high magnetic field. And we can routinely produce sub-nanosecond duration X-ray bursts within a couple hundred microns of where we intend. And that's usually good enough to get to run experiments with. The problem with this design, though, is that as soon as that X-ray burst goes off, it tends to destroy the X-pinch. And you leave the machine with an open circuit in its load region. And it's still trying to drive current through what it sees as an inductive load. So you get a lot of electrons flying through a vacuum gap that produce a shower of X-rays that you really don't want to deal with. So the final advancement on this is something called a hybrid X-pinch. What we do is we replace the supporting structure of the X-pinch with these solid tungsten cones. So they kind of look about the same. But we have a single fine wire that runs in between this gap. So the advantages here are twofold. First, it's very easy for a grad student to build these things because you only have one wire to deal with. And second, we can control the size of that gap so that, well, what happens when the device fires is that we get surface plasma all along these tungsten electrodes. And if you set that gap correctly, you can time it so that all that surface plasma floods into the gap and shorts the device out just after the X-ray burst. And so instead of leaving the machine with an open circuit, we then leave it with a short circuit that can handle the rest of the current. So you can get very clean X-ray bursts out of these devices. So we have now a device that can create excellent X-ray bursts for us. What are we going to be using those things to look at? So that's going to be, these are some absorption transitions that we're going to be looking for. On the left, we see a simple resonance transition. In this case, we have an aluminum nucleus with a single electron orbiting in the lowest energy level. To move, and a resonance transition just moves that up to the n equals 2 orbital. So that takes 1,729 electron volts for an aluminum atom. A satellite transition is the electron moves from exactly the same place to the same location, except that we now have this extra electron sitting down here. So that serves to screen the nuclear charge slightly and reduces the energy needed for the transition. So we now drop 20 electron volts to 1709. And then if you take this all the way to neutral, you have an aluminum atom with 13 electrons running around the nucleus. And in this case, a K-edge transition kicks an electron from the innermost shell all the way out into the continuum. And that takes 1,562 electron volts. So what you can see is that we're getting a range of transitions or families of transitions that will all appear relatively close to each other. So how do you see those? So that's done with a standard absorption spectroscopy setup here. On the left, we have a source of X-rays, which will be the hybrid pinch from my experiments. We have some sort of sample that we're trying to look at. And then on the right, we'll have a crystal that will disperse the spectral into its spectral components and collect everything on the detector. So there's a few requirements that need to be met for this kind of experiment to work. First, the source needs to be very uniform spectrally speaking. We don't want, say, twice as many blue X-rays as red X-rays, otherwise interpretation becomes very difficult. Secondly, the sample needs to be spatially uniform. If you have probing X-rays going through the top of this sample, and they see different plasma parameters than X-rays going through the bottom of the sample, it's almost impossible to understand what you get on the detector. So you really need to you need to have a way to enforce this spatial uniformity. And finally, if your sample gets too hot, it's going to radiate at the same energies as photons are being absorbed. So those end up filling in the absorption features that you see on your detector. And so typically this is done with relatively cold plasma samples, tens of eV, say. The problem with this setup is that we have a lot of plasmas at LPS that are completely incompatible with these requirements, specifically the spatial uniformity. So plasmas at LPS are typically cylindrically symmetric because we're using currents and magnetic fields to confine them. So on the left, we have a plasma jet. It starts as an aluminum foil here with a cathode pin in the center, and we have jets that shoot up into the experimental chamber. We also have imploding liners, which are essentially just aluminum cans that are being driven by current, so the current crushes these cans. And then we have gas puffs that are fired into the machine, and current is run through these. In every case, these are all cylindrically symmetric, and you can't probe them with absorption spectroscopy, which is a real shame because it has such a wide range of parameters that it can diagnose. So the motivation for the work really has been to find a way to apply absorption spectroscopy to most of the plasmas that we use at LPS. So to do that, I needed to build a new spectrometer and come up with a new geometry. So there's quickly some requirements on this. First, we want to use the same machine to drive the source of X-rays and the plasma that we're going to be studying. Practically speaking, this means keep everything as close together as you can. That keeps machine inductance down, and so it doesn't have trouble pushing current through the system. Secondly, we want to separate the absorption spectrum and the emission lines. I said earlier, if your plasma gets too hot, then you get everything kind of overlapping on top of each other. If we could find a way to fix that, that would be fantastic, and I'll detail how we do that in the next slide. So what we have here is a spectrometer based along an elliptical arc. So we have the source at one focal location. We have the sample at the second focus. And in contrast to the setup I showed you 2 slides back, the X-rays go from the source to the crystal first, and then they get refocused back to the sample. In the previous slide, we go from source sample, and then we go to the crystal. The advantage here is that we can use the crystal to refocus the X-rays back down through the sample. So instead of having to deal with cylindrical symmetry, we now actually require cylindrical symmetry because all of these probing rays are coming in a radial direction. And then finally, we have a film down at the bottom that will collect spectral information and also spatial information along the central axis of our plasma that we're studying. So the curvature of the crystal is one of the very unique features of this design. In the plane of the page here, it's sitting on an arc of an ellipse, and that arc is chosen to reflect certain wavelengths that we're interested in. To define the 2-dimensional surface of this crystal that we actually want to use, we'll take that arc and we revolve it around this 45-degree line, kind of in a cylindrical manner. What this creates is an astigmatic focusing scheme, where we have a focal line in and out of the page at the sample, and that's aligned with our sample axis. And then we also have a focus down here called a sagittal focus. The reason that we do this is that we can then put an aperture around the sagittal focus and only permit the absorption spectra to make it through. If the sample is then allowed to get hot and it radiates, most of that radiation is going to be blocked by the aperture. And additionally, anything that does make it through hasn't interacted with the crystal, so it's not dispersed into its individual components. So it shows up as a uniform background, not as it doesn't fill in the absorption features that we were trying to study. So to verify that the design works, we did some X-ray ray tracing. We verified that we can see from 8.2 to 9.5 angstroms. This coincides with transitions of magnesium ions that will be used for diagnostic purposes in our plasmas. We can see the astigmatic focusing, so there's a kind of make out that there's a vertical focus here at the sample location, and if you'll trust me, there is a focus on this first gray plane here. This was the sagittal focus. And then finally, the pattern on the detector shows spectral information and spatial information, as we expected. And this was done assuming a mica crystal operating in the second order of reflections. We also ran some prism spec calculations to make sure that the plasma was going to kind of play ball with us and everything was going to work out. So we ran simulations of an aluminum 5056 alloy that has 5% magnesium content. And like I said, we tuned for magnesium ions, so these are what we're hoping to see. At 10, 20, and 30 electron volts, you can see plots here. And as we increase temperature, the population of the various satellite ions change. But at all times, we can see that we have roughly 50% absorption, which should be plenty to be seen on our films. And ion density was 1 × 10 to the 20 particles per cubic centimeter. Let's see. So another nice thing about the design of this spectrometer is that we have an unobstructed line of sight between the source and the sample. So we can then put radiography off to the right and use the source of X-rays for point projection radiographs. Here we have just a single exploding wire that we were looking at. And what we can use is use this aluminum step wedge on the left to calibrate the grayscale values to a known areal density. We can then take the areal density, run that through an Abel inversion, and we can get a volumetric density profile as a function of radius for our target plasma here. And there's no way anybody can read this, but that is 10 to the 21 there. So our calculation was somewhere around this level, which is not so far off from what we've actually got. So we thought everything should be just fine. We don't see any absorption lines whatsoever in this experiment. So what happened? To figure this out, we go back to a standard setup, and we use a KAP crystal that we have in the lab. And this is really nice because it gives us large bandwidth to kind of survey the surrounding spectral neighborhood and try to figure out what's going on. Perhaps we can see some other spectral lines that will give us clues as to why we didn't find anything before. The results of that are here. So what you can see is we're using 2 aluminum wires here. So this is the spatial direction. Energy is increasing from left to right. And they were initially spaced by about a millimeter between them. And what you can pick out is very faintly, you can see resonance transitions in the magnesium ions here, but the satellite lines that we were looking for should be right in this space. And there's nothing going on. The initial thought was that maybe the plasma was too cold, but we do see a lot of aluminum features and aluminum satellite lines showing up over here, so we know that the plasma is getting hot. Perhaps these wires didn't have 5% magnesium content. We really don't have a good explanation for what happened here. But regardless, the decision was made to walk away from the magnesium ions and then say, well, we've got aluminum lines. Let's look at those and just use those for diagnostic purposes and try to study things. So that's what we did. Unfortunately, that means that we had to fabricate an entirely new crystal. So instead of looking from about 8.4 to 9.5 angstroms, we're down to 7.6 to 8.6, and kind of bracketing all the interesting features that should show up in aluminum. We should see the 2p to 1s transitions here. This aluminum K-edge should have some interesting physics in it, and there perhaps are some other lines that will show up down here for our 3p to 1s transitions. So we went through the whole process of picking a new elliptical curve, building new crystals, mounting everything, and we get nothing again. So what happened this time? The problem is this term n in Bragg's law. Different crystals will allow n to be different values. So we used mica because it's reasonably priced at about $60 a piece. And we were planning everything to be done in the second order. But mica reflects exceptionally well in first, second, third, and fifth orders. And if you've got a nice broadband source of X-rays like the pinch, well, then fifth order reflections fall in exactly the same place in your detector as second order reflections. This was identified early on in the design of the experiment, but we had hoped that through clever use of filter combinations and carefully selecting our source materials that we could effectively only see the second order. But at this point, we kind of realized that we may have overestimated our ability to do that. So what we do is we switch to a different type of crystal. We switch to quartz. And quartz has the property that it only reflects in the first order. The problem is that it's very expensive to make. So we only have one or two of these in the lab, and they're not the right geometry for the elliptical spectrometer. But regardless, we do see a nice aluminum wire here. We see line absorption in the hot corona around the wire, and we see a structured K-edge here, which is slightly shifted from the aluminum filter K-edge up here. So there's a lot of interesting information going on here. But at this point, the decision was made to kind of pivot away from that elliptical spectrometer design because it would be prohibitively costly to try to do it with quartz. And generally the crystals, because I said that everything is so compact, the crystals get damaged in the shot. With quartz being a couple $1,000s for a simple geometry, the price would have been terribly high here. So the decision was made to let's see what we can just get out of what we have here. So if we look carefully at the K-edge, in blue we can see this is the profile of the K-edge in the cold aluminum filter, and the green is the profile that's seen in the core of the wire. And perhaps if you squint a little bit, you can see that the slope of the green falls over a little bit. It definitely shifts in energy, and there's some fine structure up here near the top. All of this is diagnostic, and so all of this will let us get some information about what's going on in the wire core. We can get temperature from the slope and the shift in the K-edge, and then by comparing absolute transmission values to the known aluminum filter, we can estimate density. And so what we can do then is we can fire multiple shots, and we can collect kind of a time history of what's going on with this wire core. So we can control when the X-ray bursts go off, so we can catch absorption spectra at, say, halfway up the current drive. We can go 3/4 up the current drive and at peak current and see how everything's changing. Similarly, we can do the same thing with the line absorption. In blue, we have a line out of that absorption spectrum that I showed you before, very close to the wire core. And in green, we have it much further away. And you can see that populations of ions shift. If you zoom in and really study the fine details of these lines, you can see that the widths change. And so what this really tells us, this gives us information about the temperature and the density of what's going on in the corona around the wire. So this is more diagnostic information that we can get a hold of. And then finally, we also track current running through just that single wire that we're studying. And actually, more accurately, we measure the derivative of the current, so di by dt. And that's what's plotted here in green. And predictably, at about 15 nanoseconds into the current drive, with this time labeled T0, we see a large spike in the amount of current that's flowing through the experiment. and that's believed to correspond to the formation of this corona. So during this little bump here, we're going from the solid to the liquid to the gas phase, and then as soon as we ionize any of the material, the resistance drops and current starts to flow very rapidly. So the idea is that if we could integrate the total energy deposited in the wire during this time, we can determine how much energy perhaps is in the wire at the time when the corona forms. So we can estimate, we have temperature now and density of the core of the wire at the beginning of the experiment, and then we can, at time t sub x, when the X-ray burst goes off, we get absorption spectra that give us temperature and density later in time. And we can shift this blue pulse further and later in the current to kind of build up a time history. So the question we're asking right now is, how is energy distributed through this wire during the course of the experiment? So we get energy deposition in the core at time t0 for each experiment, and we also get it at some later time. So up to this point, we've been able to collect a time history of what's going on for the second half of the drive pulse. That's halfway up the current drive. We can't get it earlier because pinches do not like to pinch early in time. So it takes them about 50 nanoseconds to really get going. We could perhaps couple a second pulse power driver to the experiment, but that's really something that's infeasible considering the size of these things are like 2 or 3 of those desks. And we just don't have extra ones floating around. So does the core energy change is what we're asking. If no, then energy deposition must stop in the core when this corona forms. So all the current must move from that core out to the larger radius corona, and then everything stops. The more interesting answer is yes, perhaps we do see a change in the energy sitting in the core. That could be done by the magnetic field doing some compression work, some PDV work. Perhaps there is some current that lags behind in the core. It may take some time for that current to move out, or the resistivities don't shift so much that everything moves into the corona. Or perhaps there's some thermal transport mechanism that's working to move heat from the corona back into the core. These are things that we are actively looking into right now, and I don't have a really definitive answer for you one way or the other just yet. So that's what I have so far, and with that I will take any questions. Thank you very much.